Hello and welcome. My name is Mohammed Hussein Bannour and I'm going to be your instructor in this video. In this lesson, we will learn how to streamline and automatize the repetitive tasks when we're analyzing data and using ggplot2 to do that. The idea basically is to define and investigate where the repetition happen in our processes and then leverage functional programming to automatize those processes. Let's begin. Before we start, I'd like to show you the result of this lesson. Eventually, by the end of this lesson, we will be able to create plots like this. And believe it or not, these plots were created with one single command. We did not create these plots separately. So as for the learning objectives, please feel free to pause the screen here or check the code long RMD file if you're following from that file and take a look at that. For us, the objectives are fourfold. One, we would like to be able to recognize repetitive filtering and plotting in our data, create a custom function to do that, iterate those plotting tasks, and eventually be able to use nested loops to automate the entire processes. As for the packages, we are going to use mainly three packages: the meta package of the Tidyverse, the package here, and the package glue. You can pause the screen here to basically familiarize yourself with what each package is for. I'm going to run this command and load the package as we speak. As for the dataset, today's dataset is about HIV in Malawi. This is a subnational HIV epidemic indicators that has been estimated with the Naomi estimation model. You can pause the screen and also check the link that's provided in this section to discover more about this dataset. For the purposes of this lesson, we created a small data set and prepared it in a specific way, and we are going to load it using this command. And as you can see, this data set contains area level, area name, sex, age group, indicators, indicator label, and then some statistical property of that indicator. As for the details for our dataset contains mainly four pillars: the geographic area, demographic information, the HIV indicator, and the statistical measures. For the geographic area, we have mainly two variables. Variable one is the area level, which is the administrative unit, either country, region, or district. And then we have the area name, which is the name of the area level observed in that observation in our data. Then we have the demographic information pillar containing basically two variables, the age group and the sex. And then we have the HIV indicator, which has basically two variables: the indicator, which contains basically shortcode to access that indicator faster, and indicator label with the full name of the indicator we're looking at in our observations. And lastly, we have the statistical measures, which are the properties of the estimated indicators in that region. So basically that summarizes the entire structure of our data. Again, you feel free to pause the screen and access your RMD code long file to check the link here to know more about this dataset and all the properties and the statistical properties and methodologies used to estimate it. Now let's dig into more details of our dataset. So basically, let's try to estimate HIV prevalence nationally using this dataset. Basically, we'll use ggplot2 and geomcall to do this. Theme minimal is basically used for aesthetic reasons. So we can dig deeper into this dataset by simply starting to visualize the dynamics between its variables. And one of the easiest things to see is the distribution of HIV prevalence across genders and age groups. And we can do that using the data that we just uploaded. So let's take look back again at the data we have, and it looks something like this. And what we are going to do is the following. Basically, we are going to filter the area level to country, which means we are at national level, and then we are going to select the indicator that we would like to see, and which is the HIV prevalence. And then we will construct our plot using ggplot and geom call, which is basically, it allows us basically to create bar plot in a simple way. So let's dig in. The first thing we said we are going to do is area level. So area level equal country, and then we will select our indicator, and you'll say indicator equals prevalence. Now we can go to the aesthetics part in ggplot, and we can say x equals age group and y equals mean, which is basically the average estimation of the HIV prevalence. And then we would like to visualize each gender on its own. So basically we will fill and separate those bar plots using fill equals sex, so we can see each gender in a different color. As for geom call, we will use position equals dodge, so we can have each gender bar separated for each age group. And we can run this code, and we will have this beautiful plot in here. And as you can see, it provides us some insights on how the HIV prevalence is distributed across age groups and across sex in Malawi. But as you can see, we have a slight of an issue in here, which is the 5 to 9 age group that is in the middle of 45 to 49 and 50 to 54, as you can see in here. And this is a problem, and this is not supposed to be here. This age group is supposed to be after 0 to 5. It's supposed to be the second age group, not in this place. So we should fix that. In order to fix this, we need to do basically two things. One, we need to discover what kind of unique values we have in our variable age group, and then we need to order those variables in a specific order. Then finally, in the last part, we will need to re-level the order that we have in our variable. So the first thing we should do is to check the unique values of our variable. So this is our data set, and all I'm going to say is pool. This will pool simply a vector of values from a specific variable, and that variable is age group. So if I run this, let me fix this very quickly. If I ran this, you can see that it's giving me all the values, but I don't need that. I want to see the unique values. And if I do this, I say unique. If I run this code, now I will have all the unique values of my age group variable. And fortunately for us, these values are ordered already. You can see that the 5 to 9 years old age group is right where it needs to be. So we can use this to order our data. So we can come in here in this second code chunk and basically create this ordered age group vector, which is basically the same thing as this one. We are going to say pool, again, age group, and then unique. Once we do that, let me run this really quick. Now that we have a vector with ordered values of our variable, we can go ahead and basically implement those orders into our tables. And the way to do this is to use mutate and a function from the forcats package called fct relevel. Basically what we're going to do is to take that variable, transform it into a factor variable, and then keep that order throughout the dataset. And the way to do it is by writing this. We say we take our dataset that we are going to assign it to the HIV Malawi dataset that we will use later, and then say HIV Malawi age sex mutate age group, and in here we will say equals forcats, and then we will say fct relevel. And the way we are going to relevel, we'll say relevel the variable age group using the vector ordered age groups. Now we run this code. Now if we try to rerun the same code for plotting the age group distribution for HIV prevalence, we will have this plot now. And as you can see, releveling the age group variable allowed us to put this age group right where it belongs, and this graph is what we want to see basically. If you notice in this graph, we find a specific trend that describes or basically depicts the gender disparity in about HIV prevalence. So basically there's a shift between the prevalence between males and females in Malawi that happens around the age group 50 to 54. Before that, women are more susceptible to HIV, and after that it's males who are more susceptible to HIV. Now these small observations that we've seen in our plot requires deeper and more investigation. The best way to do this is to dive deeper into subnational level, into regions and then districts. And as you can see in here, we have the map of Malawi with its regions and districts. As you can see, we have 3 main regions, and each one has a few districts. Our plot describes some kind of disparities, and the best way to move forward from those observations is to dig deeper into the sub-regional level for HIV prevalence in Malawi. As you can see in this map, we have basically 3 regions, and in each region we will have some districts, and that basically describe the entire administrative decomposition of Malawi. Our focus will be basically to analyze these 3 regions as the first administrative level. So basically what we want to do, for example, is to create a plot, the same plot that we've done earlier, but this time for the northern region. And the way to do this is to adapt that code for the plot that we've done and changing the area level filter to country, and simply add the region's name in the area name that we will add. We need to add that filter, and that basically allows us to create the same plot for the northern region. So as you can see here, we have our data with all the age groups ordered. Now we have our filter, and what we can say here is area level is not country anymore, but rather it's region, and then area name is northern, and our indicator that we would like to visualize is prevalence. So if we run this code, we will have the following plot, which indicates a slight difference in the shift between HIV prevalence for males and females, and that shift that we've seen that happens around 50-54 in the age group of 50-54, this time happens in northern region. It happens more often to 45-59. Now we can basically move on and do the same thing for the rest of the regions. So for region 2, which is the southern region, we can simply change the area name with the same code and say southern. That's the southern region. And then we go to the next one, which is the central region. And like this, we will have basically 2 plots. As you can see here from our output, that's the central region. This shift persists again. It's similar to the northern one. And for the southern region, the shift is closer to the national level. So what's the take here? Basically, it's twofold. Since we have only 3 regions, it's very easy for us to simply repeat this task and change the filter from one region to another. It's not really an issue. But if we do have multiple regions, 20 regions, for example, it will be quite annoying to do that manually and honestly time consuming. There are a few ways to mitigate that, and one way to do it is by faceting or by using functional programming. So for faceting, it's quite straightforward because it allows us to break down, for example, in our case, the regions by region name or by district. But the only issue with this approach is that it works with small number of regions, for example, but if we do that for a larger number, we will have basically an unreadable plot. Because they will cite all the regions together, and it will be quite unproductive or counterproductive to do that. But we can try either ways because we still have only 3 regions. So we can basically just say facet wrap. This is the same code, by the way. We just filtered by region and have prevalence, and we will basically say facet wrap and simply ask ggplot to facet by area name. And since we only filtered by regions, we won't have some kind of confusion between national level and sub-level. So this will work like a charm. So as you can see in this plot, basically we regenerated the same plots that we've done. The good thing in this approach that we can basically compare the intensity by comparing the length of the bars. But the downside is that we lose some readability, especially if you see in the x-axis the age groups are a little bit mashed together, and that's not what we want to see in our plots. Now, before we move on to the next section, please take a minute here and pause your screen and try to answer this question. The first step to automation is basically to create a plotting function. And the way to do that is to basically create some kind of functionality that allows us to filter the data within the function that automatically plots that subset of the data that we want. As you can see here, this is basically the same somewhat code from the previous section. Basically, it allows us to visualize the distribution of HIV prevalence across age groups and sex. in this case across regions, but the only twist in this function that it allows us to visualize a specific region, and the way to do that is to specify that in the filter before the visualization. And to do this, we simply say area name equals region name, but we need to put the region name variable in between brackets like this, but not just one, two brackets. These double brackets basically tells the function filter to not use the word region name, but rather to use the input region name that is inputted within the function when used. We are going to do the same thing as well, but for the title, just so we can differentiate the plots if we use them multiple times. It's the same thing, double brackets and region name. And then we run our function to save it to our environment. Now that we have our function ready, we can basically use this function to visualize the northern, southern, and central regions simply by adding the name of those regions as an argument for the plot region function. And if we do this, we will have the following graphs. This is for the central, this is for the southern, and this is for the northern areas. This is way easier and way more efficient to do rather than to create the same code for all the regions. So one function to rule them all. So to summarize, to do our repetitive plotting efficiently, we basically create a function that takes an argument, and that argument is what we filter our data with and allows us to create subsets of data and basically alleviate all the copy and pasting and the long codes. Basically create a function that rules them all. Also, one observation that we could have observed is that we have slightly higher prevalence in the southern region, and that might require deeper investigation and analysis. Now, before we move on, I would like to discuss the glue function. Moving on, as you can see, the only difference between these plots is basically the title. And that's quite disappointing because in this case we cannot add more details in the title. Now, to mitigate this, we can basically use glue, and the way to do it is basically go to the title here and use the function glue. And within that function, we can put our title. However, the twist is to use not double bracket but single bracket within the text within the function glue to indicate for the glue function and the entire the plot region 2 function to use the argument from the function. And in this case, HIV prevalence by age and sex in brackets region name region. And now if we run this code, we will run it with the central region. You can see that the title changed, and now we have the name of the region included with a more detailed and sophisticated title. Now, kindly take a moment to think about this practice question. Moving on, since we have various indicators, it would make sense to customize our plot function to account for these indicators. Also, it would also make sense to allow our function to filter both by region and district. So basically, the idea is to create more flexibility around the function, and it's quite feasible. Let's see how to do it. This skeleton function is basically based on the previous one, but with few different changes. For example, the first change is that we will use three parameters rather than one or two. So the first one is area name, the second is area level, and the third is the HIV indicator. Once we do that, we can go on to the filtering area, and we can say with double curls like so, that area level will take the value of the function of the parameter area level. Same thing for area name. For area name, this filter will take the value of the parameter area name also, and for the indicator, it will take the value of the parameter HIV indicator. I made a mistake. This should be this. So basically, with the filtering done, we can do this also with the title within the glue function. So the mean that is regarding the HIV indicator, so we'll add that. This allows the glue function to basically look at the parameter rather than the string. Same thing with age group in region level, or area name rather. And we will also add area level for further clarity. So that's our function. Now we can basically check more the intricacies of the change in the variables within the regions and within districts and even at national level. So basically we can run these couple of functions, and eventually we will have this. This is the mean population by age in southern region Malawi. This is amazing. This is great. Basically, we automated the creation of this plot with one function. Not only that, we also were able to create this plot, which depicts the mean ART coverage by age group in Chitipa district in Malawi. All we had to do is add more flexibility to the filter, and voila. What we achieved with the previous function is a complete automation and saving of time and effort, and basically we eliminated a lot of the manual intervention by any kind of user. All you have to do is basically mention the region, the area level, and the indicator that you'd like to see, and you have what you have. But we still have some limitation despite all of our efforts, and that's basically related to the amount of districts that we have. So basically, if we want to visualize multiple indicators over multiple districts, over multiple regions, and you want to do all of that, that will still take time to generate that code. Basically, you will use this function, yeah, that's correct, but you will use that function multiple times for each district, and that is still doesn't totally solve the problem. This is basically what we mean by not solving the problem, because as you can see, these are different combinations of what we want to see, and it's not quite helpful to write some kind of code like this. Actually, I'm even afraid to run this code. So how do we mitigate this? I have the answer. It's using loops or map. Basically, we will leverage functional programming for this. The idea here is based on the function map from the package per. part of the Tidyverse meta package. As you can see here, map is a function that takes a vector or a list or any iterative vectorized object in R and apply to each element of that object a function f. The idea eventually is, instead of writing that function for each element, if you have, for example, a list of districts, let's say, and you want to apply a function to use that list of district and pass them through a function, the same way we wanted to do with our previous function. Instead of doing that manually, map allows us to basically fill in the arguments of the function with that vector automatically. Eventually, with mapping that vector or list object to the function, we will have a list of objects where each object is the result of that function. In order to demonstrate how it works, we'll use a small, funny example. So in this function, basically, we glue the word doctor with an argument full name. Basically, we want to add the word doctor to some name. We created this function. I will run it like this. This is my name, and I added doctor since I'm a PhD student, and that's eventually what I want to accomplish in the coming years. The same thing we would like to do with other names. For example, our colleagues here, Imad and Kenny. Let's put them all in a vector and apply this function to each of them. Instead of doing that manually, we can simply use map from the per package to do just that. And the way to do it is to pass a vector of PhD students with the function add doctor. And once we do that, we have our output in the form of a list. You might ask yourself, how do you access the elements of the list output of this map function? Well, it's quite simple. Since it's a list, we simply use the double brackets or brackets. I'm actually quite confused, but this operator basically, which is quite different from the operator we use in the functions. So if I save this function the same way we did in the previous chunk, if we save it to PhD grads and then access PhD grads, we will have like three list elements. My name with the doctor attached to it, and then my colleague Ahmad, and then my colleague Kenny, and they're all doctors, bless them. Now, what if we want to access the second element? We simply put two within these double brackets, and we have access to that element. Easy. We can leverage the same principles that we've seen earlier to automatize the creation of our plots on sub-regional level, on sub-national level, in the regional level. Also, we can do that at sub-regional level, but we will get to that later on. The first thing we can do is to create a vector with the region names, and that's what we've done in this line. Next, we take that region, that vector, region names, and then we pipe it to our map function. And within this map function, we will do two things. One, we will tell map what function we want to map through these region names, and second, we will tell map what kind of arguments we want to use for our function that will be mapped. So just notice here that when I will add the plot Malawi function, I do not use the brackets or the brackets at the end of the function to depict that this is in fact a function. I just leave it like that. This is actually the syntax. I know it's quite confusing, but it's the way it works. Now, after that, we add region, the first argument, and then the second argument will be prevalence. And if I run this function, I will have three plots. This one, mean prevalence by age in northern region, this one for the central, and this one for southern region. And all of this was done by one line of code. Now, kindly take a minute and think about this practice question. Since analyzing the geographical implications of epidemiological disease patterns is very vital for the epidemiological analysis, it makes sense to basically do that on the most lower level of administrative decomposition of an area. So basically, the objective of this comment section is to create a helper function that allows us to access any kind of administrative level. Basically, we will create a function that allows us to access all the regions and all the districts within them just by specifying what area level we want to check and what region we want to check it in. Let's start by creating a vector for district names. Basically, we will take our data and filter by area level equals district, as you can see in this line. Then we pull that vector and only keep the unique values. Once we do that, as you can see, we have all the district names. Note here that the idea eventually is, since in the last time we started by creating a vector of regions, the idea here is to automatize that process as well, so we don't have to create a vector to map over every time. So once we have that, it's done and ready. Now, we can do that by creating a function, and the way to do it, basically, as we can see later, is to take the previous code that we've seen and just plug it into a function, and within that function we simply add or construct our parameters. The idea finally is to automatize the part where we specify which regions we want our function to map over. As you can see here, especially in this part of the code, this is basically the same code as the previous one, with only difference in this part. To make this function work for our purposes, we basically create the filter to basically filter according to the level parameter. So we add that with double brackets, and basically we can save this function like this, and then we can run this function with the area level at region. So once we hit that, we can basically have all the three regions. So instead of writing a vector, we write a small function, and from that small function we can extract the regions, and we can also extract the districts. So we have basically 23, 4, 5, 6, 7, 8, 28 districts in this data set. To basically create a vector of 28 districts, that's not something that you want to do over and over. So the idea basically is to automatize and streamline these practices. We create a small function that can get us either the names of the region or the names of the districts, and that allows us to basically facilitate our automation process for going further. Now we can move on to use the area level function to facilitate the mapping of the plot Malawi function. So basically the way to do it, in this chunk we want to plot incidence for all regions, and the way to do it is to specify from the area level function that we want to see only regions. So we type region, and then in the map function we have our plot Malawi function. This is the function that we want to map over all the regions, and now we can simply add our we can now add our arguments. First, the first argument is region. That's the one that we will filter with, and then we will also want to see indicator incidence. Now we can run this code and we'll have three plots, each one for each region. Now we can leverage the area level function, the map function, and the plot Malawi function all together. Now, how to do this? First, let's say, for example, we want to plot the incidence indicator for all regions. The way to do it is to get a vector of regions and then map the function plot Malawi over all those elements in that vector. Also, we should not forget to specify, properly specify the arguments for the plot Malawi function. Now, we can do this by specifying in the area level function that we want to have to see all the regions, and then in the map function we will also specify our arguments. The first one that we want to use the regions as well, and we want to see the indicator incidence. Once we run this code, we will have three plots. Each one is for each region in our dataset. Once we run the code, we will have basically three plots. Each one is for each region in our dataset. Eventually, we went from automatizing these plots from 2 lines for 3 plots to 1 line for 3 plots. But I bet we can do better. What if we want to plot HIV awareness, the HIV awareness indicator for all districts? Well, we can do that as well. The way to do it is to specify in the area level that we want to see district level. This will allow us to have this vector of districts, this one. And once we have this vector, we will map over this vector the function plot Malawi that will get the following argument. First, district argument, and then we will tell our function to use this aware PL HIV prop argument, and this is basically the variable that not the variable but rather the indicator that depicts the HIV awareness variable. Once we run this, we will have multiple plots, as you can see here, and it's still running. Actually, we have all these plots. We don't 28 plots. We only run the code once, and this allows us to save lots of times, a lot of time, and this is exactly the objective of this lesson. Now, maybe you have different priorities and you would like, for example, to visualize the multiple response variables, that those indicators you want to see all of them according to all of the districts, for example. This might become cumbersome because if you have, for example, 10 indicators, and you will have to create again, do the same lines over and over where you get the data for the regions or the district and then pass the map function and specify what kind of indicator. And if you have 10, 20 indicators, then it becomes quite a repetitive task, and it's the automating ggplot lesson, so we need to automate that as well. And one way to do it is to create a nested loop, where in the outside part of the loop we basically iterate through indicators, and within that loop we basically run the same code as previously. We take the regions, we map the plot Malawi function through these regions, and we indicate basically within the map function that we will use the indicator from the loop. I know it's a little bit quite confusing in the beginning, but it's quite straightforward. We can start off and create multiple plots, automatize plotting for regional level for 2 indicators, for example. In our case, it's the PLH IV and the prevalence indicators, and we can do that with our nested loop. The first thing we do is basically to create this vector of indicators. As you can see, we have two indicators, and then we will have to loop over them. And the way to do it is to say, for I in 1, that's the first element of the vector, for I in 1 to length indicator, we will go to area level by region, and then we will map through that vector our plot Malawi function regionally, and we will use the indicators I element of the indicators object. So basically what we're saying is, for each indicator, create me all the plots for the region. Now, if we run this code, we will basically have that. So mean prevalence by age group in southern region, and if we go up here, mean PLHIV by age group in northern region, and the same thing for the central, southern, northern, again central and southern. So we have basically all six plots in our disposal. Of course, this is not the only combination. We can do that for all the indicators we have, and for all the regions and all the district. For the district case, we only have to change region with district. Literally, that's all we have to change. And we have 28, for example, if you have two indicators, like in this case, and we have 28 districts, so 28 times 2, we will find ourselves with around 56 plots for this. So this far, we were able to basically create these functions, and we were able to nest them within a map, and then nest them within a loop, and be able to automatize the entire process, and be able to see all the indicators for all regional levels. Now we still have to finalize this and make it a little bit more pretty, and also save it. Now let's revisit our very initial code from this lesson, and this is basically the code where we filtered by country, an area level, and prevalence and indicator, and basically visualized the mean prevalence over age groups and sex. And when we do that, this is basically what we have. Very simple, yet it allows us to understand a lot of what's going on. However, we can make this better. We can refine the aesthetics of this plot and basically go on and make sure that it can also account for other filtering areas like the ones we've seen later. But first, let's try and make the code more organic and accommodating for aesthetics that might be quite more interesting to see. As you can see here, we have this new graph. Let me show you exactly what changed here. Mainly we have three main changes. Number one, we have a change of color, and in here we used a color blind colors that allow people with difficulties to be able to see this. Secondly, we added some error bars. These error bars take advantage of the already existing data, because the data we have is an estimated data that has lower and upper bounds in the estimation process. And finally, we have these the legend box, which is usually on the side outside of the plot box, but in here we added to the plot box to basically avoid missing space or wasted space. So these basically are the changes. Next, we are going to take all of the code, comment it out, and then add it layer by layer until we finish everything and we get this this plot. So let's start with that. So here's the code that we have. At first, it looks a little bit overwhelming and confusing, and it might be, honestly, but take a deep breath. It's fine. We will go line by line. It's not that complicated. So first of all, let me comment out everything down here. Okay? And this as well. So basically, this is the code, and I commented out everything up to geom error bar. Let's figure out what this incremented code means, and we can go from there. First, we take our data, HIV Malawi, we filter it by prevalence and indicator equals prevalence and area name equals Malawi. So basically, we want to see the prevalence level at country level, and then we pass that to ggplot, where we emphasize on the aesthetics. And here we will pass all the aesthetics all together just for the space, so you can see everything. For the x-axis, in the geom call, we will have the H group and then the mean for the y-axis, and we will differentiate the color in each bar by sex. And then we will pass the y-min and y-max arguments that will be used by the geom error bar. For the y-min, we will use the lower variable, and for the y-max argument, we will use the upper variable in our data. Once we have that, we can add another layer of geom call, and in here we emphasized on the position equal position dodge. This is equivalent to using position equals quoted dodge, but this helps us to differentiate better the bars in the bar plot. We've done the same thing for the geom error bar, which is the function that allows us to create these error bars. We also specify their width and the line width of these error bars. Once we hit enter, you can see that this is a closer and closer version to the final version that you've seen earlier. This still doesn't have a title or a subtitle. The colors are still not modified. The axis titles or the axis labels are still not very well taken care of. And the same thing with the legend. It's still on the side, not on the top left hand side inside the plot. So we can change that, and the way to do it is to modify a few aspects in this plot. Now I removed the comments from these 3 lines, and I added this line of dashes just to differentiate where we was and where we're going. Now from our code that we explained, I will add the plus sign so that we relate this code to this one and move from there. This line, the scale y continuous, specifically allow us to use and manipulate the y-axis, and the idea here is to start the y-axis at 0 so that we have some kind of scaling or measurement ability to see where it all starts. Additionally, we will use the scale fill manual function. This function allows us to access specific layers in our plot. If you can remember, in the geom call plot, we use the fill equals sex argument. This allows us to differentiate the color that fills the bar plots by sex, and we have females and males. So in our function, skillful manual will allow us to do two things. First, change the value of the color assigned to each sex, and two, change the naming that will appear in the legend. So first, let's change the value of the colors for each value for in our sex variable. So we assign this vector to the argument values, where we have female assigned this color and the male category assigned this color. These are hexagonal colors that depict specific color. We've done this before in the GT lesson. You can go back and check all details about how this works. Additionally, we will use the labels argument, and in this argument we will specify how we want the categories in our sex variable to look. So in this case, we basically tell our function to use these two variables, these two values, and these two values are the same, female and male, with just the first letter capitalized. And finally, we will use theme light, which allows us to basically see more clearly where we're at in our plotting. So let me just remove this plus because it will create us some problems, and Control Enter, and yeah, we can see that things are turning into more and more better shape. Let's continue. Next, we will talk about and figure out how to change the legend position from the right side to the top left side. And the way to do this is quite simple, frankly. Now we can change the position of the legend from the right side beside the plot to the top left corner inside the plot itself. And the way to do it is to specify a few arguments in the theme function within ggplot. The way to do it is to first start by defining the legend position, legend justification, and legend title. First, legend position, we will provide the specific coordinates within the plot where we want our legend to be, and in our case we want it to be in the left side, which is 0, but we want it to be a little bit to the right, so 0.05, and at the top, which is 1, but instead of right in the top, we want to be a little bit inside the plot, so we will specify 0.95. Then we want to anchor the legend position at the top left corner, and we will do that by specifying the legend justification argument with C01. Again, 0 is left and 1 is top, so we want it to the left top corner. And we will specify also legend title as element blank. We don't want to have a title for the legend. It's almost redundant because it's clear male, female, that's the sex of our these are the category that depict sex in our data. So once we have that and we run this code, we will have a plot that looks like this. The only issue here is that the legend box it does not have any kind of borders, so we can also add another argument where we can say that we want a dark gray line within the box of our legend, and with the width for that line at 0.5. And once we run this code, we will have corners. We will have basically a line around the area of the box of the legend box that allows us to see clearly that this is a different component in the plot. So once we do that, we can basically go on and specify the title, subtitle, and the axis titles. And the way to do this is basically by specifying these elements in the labs function in our code. We remove the comments, we add a plus here to add everything together. For the X, we will specify that we want to display age by years. This character. For Y, we will specify that we want to see the word prevalence clearly, and the title will be the age-sex distribution of HIV prevalence in Malawi. And for the subtitle, we will add the detail that these are Naomi model estimates for December 2022. And once we run this code, we will have this very beautiful, very organic plot, and this is what we were working on for the entirety of this code. So these codes allow us to create this plot. Next up, we want to make this our main function while we add the filtering process to automate it with map later on. In this code, I took the same code that we generated earlier, and I put it inside the function that takes 3 main arguments, just like the functions that we did earlier. These arguments are area name, area level, and HIV indicator. And these arguments are going to be the ones that we filter on and the ones that we add for the title to depict exactly the details of the plot. So in the filter here, we will do indicator instead of prevalence. We will use the double curlies like this, and we specify that we will filter by HIV indicator like this. For the area level, it's going to be the same thing, double curlies, area level. And for the area name, instead of Malawi, we will add the double curlies, and we will indicate that we will filter by area name, the area name argument. Everything will stay the same except for let me put this clearly first. Area name. Okay, so we have these filters. Everything is the same except for the title. In here, we will use glue. Glue will allow us to glue together the arguments that we filter with and the text itself. So we do this by gluing together the text and the arguments in our function. So age-sex distribution of HIV indicator, whatever we will place in our function, and instead of Malawi, we will add area name. Now, once we have this, we can test it. To test this function, let's first run it, and then we will add this we will run this function for the Chitipa area name, which is a district, and we will use the HIV indicator PLHIV. And once we press Ctrl Enter, we will have the following graph. And in the following graph, we can see specifically that age-sex distribution of PLHIV in Chipita. So we have the specific details of this plot with the legend in position, with the distribution in position, with the error bars in position as well. So basically, we can use this function and automatize it the same way that we automatize the previous one to get better plots. Now, similar to what we've done with Plot Malawi and the automation, we will leverage the area level function, the map function, and the Plot Malawi function to generate the previous plot, but on all the region for the prevalence indicator. And all we have to do is to specify that we want to use the regions for the area level. This will give us all the regions like this, and we will specify the arguments for the plot Malawi final. Basically, we will focus on region and prevalence. And once we do this and run this code, we will generate 3 plots. Each of these plots depicts the age-sex distribution of HIV prevalence in each region. Here we have the southern, here we have the central, and here we have the northern. Finally, the last thing that is left for us to do is to save these generated plots locally in our machines, and the way to do it is to automatize this process as well. And the best way to do this is to add the ggsave function to the plot Malawi final function, so that when we generate, we save these plots as well. As you can see here, we are creating a new function that's plot save final, and this function will basically take all these plots and save them locally using here the package that allows us to basically manipulate paths and directories and glue. So the way to do this is use the same code. We didn't change anything in this code. This is the same code, basically the same function as well. The only thing that's changing is this line. As you can see, we will use the ggsave command to save this file, and this file name will be manipulated with glue. We will use the here package to specify that we want these plots, these files to be saved in outputs, and we want these files to be saved in the GPG format. So what we do is specify with the glue function within the here function that we want to save, for example, the output of whatever indicator we choose, at whatever area level we choose, at whatever area name we choose, as GPG format in the outputs folder. This will allow us to detect all the differences and see whatever plot we want to see by its indicator and area name. So once we run this code, we can definitely start doing that. After running the function, we can use it by specifying what exact combination we want to see, and in our case we want to see the Chipeta district for the PLHIV indicator. And once we run this, it will save all the 7 images, all the 7 plots from our function to our output folder. Now, if you go to your output folder, if you didn't create that, please do and rerun the code. If you do that, you will find that plot saved in that folder. Now, we will have to basically see that throughout this lesson, we streamlined the creating the ggplot, code, and then put it into a function, streamline all the process so that it's automatized through whatever region or whatever indicator we're trying to see, and basically we also automatize the way we save those files. Now, for example, we can map over several regions and create these plots and save them at the same time using the same function and the same line of code basically. So we will use area level regions for all the regions, and then we will map plot save final function over all these regions to visualize the prevalence. And once we do that, we will have three plots that are saved in our directories. These are my local directories, so you will have the same thing in your local directory as well. Similar to that, we can do the same thing by visualizing with nested loops multiple indicators, and at the same time multiple regions through this code. We've done this previously. The only difference is that we are basically using our new function plot save final to create these new beautiful plots and also save them in our output folder. And all we have to do is to run this code, and we will have all the new plots created and saved in our output folder. Now please take some time to look at this question and figure out an answer for it. So, to wrap up our lesson, we had a ride through this lesson. Basically, we were able to create our main base ggplot graph, and then we used that to create a function that allowed us to automatize some aspects of the filtering and subsetting the data. And then we leveraged the map function from the per package from the Tidyverse to iterate the same function over various subsets and filtering in the data. We also use for loops to do that in other dimensions, as we've seen in the indicators. So we loop with the indicators, and then we map the function over multiple regions. And then we also leveraged some of the glue functionalities within this function, where we glue together strings of text with the filter text that we use to filter the data, so that we have more information on the plot itself. And finally, we were able to use the same technique with glue to save this data with here and ggsave, and this basically allowed us to automatize the entire pipeline from getting the data to basically visualizing all the dimensions in the data with few lines of code, with less effort and less time dedicated to all those manual filtering and the time it consumes to do that. So thank you. That's it for our lesson today. Thank you so much for following along and for your patience. See you in the next lesson.
For more resources, visit our website, where you can track your progress, access interactive quizzes and lesson notes, and connect with our teachers and other learners like you. And if you'd like a more guided experience, we also offer live online bootcamps with expert help. So join us at thegraphcourses.org to start your learning journey today.